Okay, let us continue with the lecture. I am recording this session. Please do not switch on your cameras or microphones. And first, we are going to repeat what we did last time. Last time, we proved with you that this rotation tensor is orthogonal. By the way, we started with you discussing orthogonal tensors, right? Orthogonal tensors are characterized by this property, right? If we transpose it and inverse it, the result does not change. We proved also in the exercises that the order of this operation, inversion and transposition, is not relevant. We can write here simply minus t, right? These tensors are very important. Also in continuum mechanics, we will discuss with you. They describe both rotations and reflections from the planes. And here we proved with you last time that rotation tensor defined in this form. Remember, we calculated with you this express this rotation tensor in terms of this rotation angle omega and unit vector E in the direction of this rotation axis. And then simply using this representation for this tensor E hat, right, in terms of two other orthonormal vectors P and Q, such that these three vectors form an orthonormal basis. We simply mathematically compose the tensors I and R transpose and show that the result is identity tensor, which means that R is an orthogonal one. But there was another more elegant proof, simple proof, namely, we showed with you that if we express R transpose, we can do it simply writing that changing angle omega to minus omega, which means that this is nothing but the rotation around the same axis but backwards, right, in the opposite direction. And it means that if we write here such an expression R transpose R, which gives us then what? It gives us the first rotation by this rotation tensor R by the angle omega around some axis E, and then backwards by the angle minus omega, which means that finally we get this vector x back, and which means that this result is nothing but the identity tensor, right? Another interesting property we proved last time with you was that if we take exponential of a skew symmetric tensor, we get orthogonal one, which establishes this relation, this connection between skew symmetric and orthogonal tensors. And as I mentioned last time, we will see also this connection with you next semester if we discuss this eigenvalue problem, because we will see today also eigenvalue of skew symmetric tensor is 0, and eigenvalue of orthogonal tensor is 1 plus or minus. But if you take exponential of 0, it will be exactly 1, which also shows this connection between these two tensors. Then we started with you discussing scalar product. We also repeated this scalar product in the exercise today, but the main idea was that we defined the scalar product by means of the tensor product of vectors, and you see the main idea that the first vector is multiplied here scalarly by the first one, the second by second scalarly. Why it's so important? Because then in this case we get, due to this form of the definition, we get this property D4, which is very important because it guarantees that the scalar product of tensor by itself is always non-negative, and then we can define also length or quadratic norm of a tensor, right? And also other properties, we know this property C are very, we call here this properties D. We prove it today with you, commutative rule, distributive rule, and associative rule for the multiplication by scalars. This was very important formula we will use in continuum mechanics, namely formula for the composition for the scalar product of a tensor by the composition of two other tensors, which can be reorganized. You see here, we move here B with transposition to the left, or C with transposition to the right. Here, the second part of the formula, and we prove this formula in two ways using this tensor product or using purely components, right? Another formula we use it today in the exercises that the scalar product of two tensors does not change if you transpose both of them, right? And based on the scalar product, we define trace of a tensor. It is simply scalar product by the identity tensor, and we saw today in the exercises how we calculate this trace using different kinds of components, homogeneous components of a tensor A or mixed components. Another important result was this formula for the trace of the tensor product and trace of the composition of two tensors can be obtained in this way. We simply compose this to take a scalar product of these two tensors A and B, taking one of them transposed, right? And finally was another important formula resulting from this commutative rule that trace AB is equal to trace BA. Very important for continuum mechanics. We will use it very frequently next semester. Next topic we discussed was decomposition of second order tensors, and first decomposition we discussed with you was the decomposition into symmetric and skew symmetric part, and this is defined in this way here. And as we discussed also today in the exercises, this tensor, symmetric tensor, skew symmetric tensor, they form not only subsets here, the subsets, but they form only subspaces. Why? Because all 8 axioms are valid separately for skew symmetric tensors, separately for symmetric ones, right? For example, sum of two symmetric tensors is symmetric one, is easy to prove. Product of a symmetric tensor by a scalar number is again a scalar number. It is again a symmetric tensor, excuse me. And what we did last time, we tried to represent this tensors with respect to a basis. We tried to find a basis and dimension of the subspace. And for the tensor M, we proved with you for symmetric tensor, we proved that if we switch the order of indices, the components are the same. That means that there is some symmetry in this matrix, and if we represent this tensor with respect to a basis, we can take separately diagonal terms and non-diagonal terms, but only one times, either above this diagonal or below, right? And here it is below, you see this summation, which means that this is basis tensors and these are basis tensors, and we count with you at all 1/2 n plus 1 these tensors which form a basis of symmetric tensors, and which means that this is the dimension. This is the dimension of the subspace of symmetric tensors. And for skew symmetric tensors, we prove with you that diagonal components are 0, and then non-diagonal components are here changed if we change the sign, right? So it means that they form a skew symmetric matrix, right? And you see here that in this case we can represent the skew symmetric tensor also in this form, but the only difference due to the fact that these non-diagonal terms are 0, this part disappears, and we have only this part with minus due to the fact here that we have here minus, right? And which means that we have only terms under the main diagonal or above. It means that the number of this basis tensors is an n times n minus 1, and this is a dimension of the subspace, right? Of skew symmetric tensors. And the next topic is that very important we start today, namely we prove we set now from now on n equal to 3, very important for continuum mechanics and this three-dimensional space. And the advantage is that in this case we can use this vector product, right? And we try to look what happens then to this skew symmetric tensors if we consider this three-dimensional space. So what we do here, we simply look, it is the same formula. It is the same formula where I simply write here 3, right? And if you do that, you remember this result, these terms, right? Gi tensor product Gj, Gj tensor product Gi. You remember another form, this formula A tensor product B minus B tensor product A, right? This skew symmetric tensors. You remember this formula? It was a formula at the end of this. I show you this formula in this from here. This formula, right? This second formula here, right? This formula. Accordingly, we can represent this term simply as a vector product B with this head, right? The head is this tensor which forms a vector product by this vector, right? And if you use this fact here for our skew symmetric tensor, we can write here Gj, Gi. You remember the order of this vector was changing here. Once more, look, it was B here. We start with B, but B is second here. A is here second, and here becomes first one. That is why here we have, if you look, we have here Gj vector product Gi, right? With this head, right? And what I do now, everything without head, I denote a vector. I denote it by this W, and then we can write W head. And this W is then everything that here, I clean a little bit there. Here, everything here, W is everything without head. This something like that, right? Everything without, this is our W and vector. And this is, I write this W vector once more here. And we will discuss with you the property and the name of this vector. By the way, what I mentioned also last time, with this formula, we prove with you that any skew symmetric tensor can be represented as a vector product. Last time, you remember, we proved with you, not last time, or maybe 2 weeks ago, something like that, we proved with you that vector product by an arbitrary vector represent a linear mapping, which is the skew symmetric tensor. We proved it with you, right? And now we show vice versa, that any skew symmetric tensor is a vector product, right? So there is one-to-one correspondence. And this is exactly this proof, because we started with an arbitrary skew symmetric tensor and show that it can be represented as a vector product, right, by some vector W. And this W has this expression. It gives, this formula gives us also an expression for this vector. This is this one. And what I don't like here, this check of this indices, right? So we sum up here only over here. This is the main diagonal. And you see we sum here over this lower left triangle, which is don't like because it's not convenient. So my idea is to sum up also here, but in this case, what happens? This Gi, we instead of Gj vector product Gi, we will have they switched, right? They will switch this order. We'll have Gi vector product Gj, but this is a negative. They will have negative value, right? And the same will happen here if we get GWJI. These components are also skew symmetric, right? You remember here we discussed with you last time, the sign changes. That means that if we consider this upper right triangle, sum up all of this, then we have the same terms because we have twice, we change sign twice here for this vector product and for this W, which means that instead of get the same result, I have to take 1/2 of it, right? 1/2 of, and then look, I can apply, don't need the sum symbol, I can apply simply summation convention, and the terms WII are 0 right here, because we proved with you, first of all, they are 0 here, and secondly, also this vector product GI, vector product GI is also 0, right? That means that these diagonal terms will be 0 and will disappear here, right? And that means that we can simply sum up, apply Einstein summation convention on checking these indices and sum up over the whole matrix, right? I going from 1 to n, clean. It is too much again here written, and here look in this here this formula we are discussing this middle formula here, and in this formula I and J are going from 1 to 3, right? From 1 to 3, right? Another possibility, and it is much nicer, although we have here double summation, but we don't need to check these indices in the first one. Another possibility is to do the following. If I represent this tensor W with respect here, with respect to this basis GI tensor product GJ, right? And then I map by GJ, I get exactly this GI. So here, this will be exactly this WI JGI. So I take another color, maybe green one. So this term here with these components, this is exactly this one what we have in this parenthesis. So it's another representation of the same formula, right? Can be useful. Another representation can be get here also if we use, you remember, for this vector product, we can use this, or this basis vector, we can use another formula, namely with the permutation symbol, which is given here. And you see that we can represent this formula also in another way. It was a formula 136, I suppose. It is not written here. Oh, it is a second. No, it is 140, right? It was 140, I suppose. This formula 140, right? And it is easy to write out this formula in three-dimensional space because there are not so many combination of indices, and if we do that, we can also write this result here in this way, right? So we go through, we have here triple summation over I and j and k, but we choose only those combinations which are non-zero, right? Odd or even permutation, and that results in this formula, and right, and this is very convenient because this is the result how to get this vector which produces vector product, and this vector has a special name, axial vector. So this is the axial vector, right? And now we have a formula. We get an exercise, some exercise we skipped last time because we are not so far. We're not so far, but you get some exercise how to calculate this. This axial vector. Let me show you. This was the exercise here. Right, yeah. So you get 147, please do this exercise. You get this tensor, skew-symmetric tensor W given in terms of these components. You see this metric we have here exactly zeros on the main diagonal, and these terms are skew-symmetric, and you have to calculate this axial vector here of this tensor. So you have to calculate this vector W small, right? Using this formula, you practice science, right? It's very useful formula. You see that we can represent this tensor W as a vector product. What we proved with you, we proved is that generally possible, right? Okay. Now what we do here, we we continue. Namely, interesting result, important is this formula here, which is clear, and which means that if you represent W as a capital tensor as a V hat, it means that here this formula means that V hat V, and this means that I go to the left, it is V vector product. It means that nothing but the vector product of a vector by itself, right? Here, right? So, and also here, right? And which should be 0. But in the language of eigenvalue problem we'll consider with you next time, it means that this vector W has also another meaning. Namely, it's a vector, it's eigenvector of the tensor W corresponding to 0 eigenvalue. We will discuss with you eigenvalue problem next semester. It is written, I give you a little bit outlook. In this form, if you multiply some tensor A by vector A and get again vector A, multiply by some number alpha, and X should not be 0 vector, because otherwise is the problem is solved trivial solution. And we have exactly here this. We take we multiply or we map our tensor W by a vector W small and get 0, which means that we can represent the 0 as a number 0 multiplied by W again, right? Which means that W is nothing but a eigenvector of this tensor W corresponding to 0 eigenvector. By the way, it helps us, this formula here, we proved with the formula for this axial vector here, help us also to calculate this eigenvector corresponding to 0 eigenvalue. So clear? Questions? You can write me in chat. Please do not ask loud this question. Only write me in chat if you have any. And now I would like to formalize this result, namely this operation. So in principle, you see what we did here. We started with arbitrary skew-symmetric tensor and got an axial vector of it, right? Axial vector by means of this operation, for example, in this way, right? And this I would like to formalize. I would like to establish, to define such operation taking axial vector. But the problem is that we cannot do it generally for any arbitrary tensor. We can do it for skew-symmetric one. That is why we define a new operation, and this operation is denoted. Look, if we before we discuss with you this operation hat, which produces a tensor which calculates this vector product, right? So once more, it was equal to W vector, right? And now I define inverse operation, right? From this skew-symmetric tensor, I get its vector W, that means it's axial vector. But I would like to do it generally to any arbitrary tensor. That is why this operation here is has this here. This is this operation, right? It has a inverse direction, and this operation means first take skew-symmetric part of a tensor, and second step take axial vector, calculate axial vector of this skew-symmetric part, because this is possible, right? Skew-symmetric part of a tensor is skew-symmetric, and that means that it produces it produces this vector product, right? And this operation means that, look, if I exactly here, I show you. So my idea is that if I look, if I take this operation here first on my tensor A, you see here, this new operation, right? Then I get I get this axial vector, and after that I again form a vector product, and that means that I come back to skew symmetric part of a tensor, right? Or another way around, the same, completely the same. Maybe it's even easier to understand this operation. So you see this is new operation. It once more take a skew symmetric part and calculate axial vector. This is then again vector product by this axial as a tensor back. We get this tensor back, but we said that we first apply skew symmetric part. That is why it is simply the same as mapping a skew symmetric part of a tensor by arbitrary vector x. So these are different definitions. Or another way around, you can understand this new operation. It's also very, very useful in continuum mechanics. We will see with you in the context of rotation momentum balance. We will discuss with you. We will discuss with you next since continuum mechanics. Also here in the tensor algebra, in the next chapter, we will formulate it with you, and we'll see how it is convenient to use operation. And this proof, we will prove with you that Cauchy stress tensor. Remember, we discussed it with you symmetric by means of this operation within two lines, right? Which will take on continuum mechanics 2 pages, right? So this is very important operation. Okay, do you have any questions to this part? And you have, we come back to this operation once more after the break. So we now make a break until 12:30, and then continue with you, and then we will work a little bit more with this operation. It's rather interesting operation, and you will get also some exercise. To this operation where you have to prove these formulas. Okay, so far no questions. Then thank you for your attention, and we make a break 2.5 hours until 12:30, and then meet again for this lecture and continue with the lecture. And today we will start. Also give you outlook. We will start with the second chapter, and we will discuss with you, start with the coordinate systems. Okay, then see you later, right?